Hello everyone and welcome to RNG Crystal tutorial. This is a module that came out on April Fools but eventually got updated, and now it's one of the extreme difficulty modules. This is the module. There are two ways to solve it. You can solve it on random or not randomly, by finding out by predicting coin tosses. To disable the music, you just unselect the module, and let's dive into how this module works. So the module randomly, or should I say not randomly, generates coin tosses, where one is represented as heads and tails is represented as zeros. So when you press this button, it starts a trial, and in here it shows the chance that this particular result can come up. The trial itself consists of repeatedly tossing the coin until it becomes a tails. So in other words, it keeps oh holy shit, I should probably why is it so laggy? Okay, 1 second. In other words, it repeatedly tosses heads until it tosses a tail. So this number, what it represents, is the chance that this particular result is present. So the way we find out what was tossed is just so the way it works is the chance is calculated like this: 1 divided by 2 to the power of n, and it is equals to the number on the display. So in our case, n is equal to 1, which means we only tossed one coin. So what we got was tails. So let's write that down. And we keep doing that. Tails. Tails. And we try to get 48 tosses this way. So this is equals to 16, which is 2 to the power of 4, which means we had 3 heads and 1 tail. And we keep doing that. By the way, one of the ways to solve the module is just randomly press this button until it generates 11 heads in a row. But that's not the way we'll usually solve it. This is taking too long. I need more heads. Zero. 0. Okay, this is 1 divided by 2 to the power of 4, which is 1110. 0, 0. Come on, too many zeros. Okay, big number, let's go. This is 15625, which is 2 to the power of 6, so we have 5 heads and 1 tail. Wow. 39065. 2 to the power of 8, so 7 heads, 1 tail. And we're over 48 tosses, so what we need is actually the last 48 tosses. We currently have 51 tosses, so we'll take the last 48. And we're going to work with that, and we don't need this anymore. Alright. So, when I said that the tosses are random, why is it like that? They're actually not very random. The way it works is there is a list called tabs. Oh, блядь. Why is it so laggy? You know what? Screw it. Let's do it here. So the way it works is we have a list called tabs. It's 24 digits long. It's a binary massive, so consists of zeros and ones. So for example, 0, 1, 0, 0, 1, so on 1, 0, and let's. This is a fixed list, which means it does not change throughout the entire thing. However, we don't know this list, and actually our goal is to find what this list is, to be able to predict the next tosses, which is, by the way, the what you need to do. Your goal is to predict the next 11 tosses on this module to solve it. But to do so, we need to know this list. And how does it work? So what it does is it takes the last 24 tosses. For example, our last 24 tosses, this somewhere around this, I don't know, pretend it's 24, and it takes from this 24 tosses, it takes digits from the positions where in the tops list it is a 1. So for example, in the tops list we have ones at 2nd position, 5th position, for example 16th position and 23rd position. So if for example, so in our case, let's count actually 3, 6, 9, 12, 15, 18, 21, 24. So in our case, it would take this one, this 0, and this 1. So 1, 1, 0, 1. And it will perform an XOR operation with all these ones, which basically means the sum modulo 2. In this case, it's a 1. And what it's going to do, it's going to add this result to the right of our flip list, and it's going to do the same thing, but this time with the next last 24 flips, using the same tops list. However, we don't know this list. Our goal is to find it. It's just an example of what would happen if the tops list was looked exactly like this. So, how are we going to do that? Actually, the main part of solving this module is going to be writing a TFC script. On profile bombs or Twitch plays bombs, you don't actually have to write it yourself. You can just use one, which I'm going to leave in the description, and basically the one that's going to be the one that is going to be finished by the end of this tutorial here. You can just use it, copy paste, and yeah, and get your answer. But if you're playing a challenge bomb or you want to learn the module properly, I'm going to actually explain mathematically how the script works and how to actually write it. It's relatively short, so it's fine. And yeah, you have to write it by your hand if you solve a challenge bomb. So let's do it step by step. First is we're going to define our flips list and copy paste the flips here. Remember to separate everything with commas. And for now, let's comment that. Is it 48 long? Oops, I see it. It's not. Wait. That's weird. 3, 6, 9, 12, 15, 18, 21, 24, 27. Wait, why is it 44? Okay, I see why. I copied the wrong thing. Once again. Okay. And put this semicolon so it just to show, if you don't put a semicolon, it displays your answer for that line. If you don't, it doesn't display. Just to save time and efficiency. Now we're going to create a matrix. So let me briefly define a few lists and and show how I'm going to write them down. So our flips list I'm going to write like this. These are the elements of this list. Matrix M is going to look like, okay, oh, I forgot. First we're going to define the, actually no, matrix M. It's going to be a square matrix sized len by len, where len is going to be equal to 24 for now, but later on we will actually decrease this number based on certain properties of this matrix until this matrix meets certain criteria. So for now we're going to write this equal to 24. And the way this matrix is structured is the first row is f1 to f len, and this is f len to f len, f2 len minus 1. So the second would be from f2 to f len plus 1. So in other words, if len was equal to 3, our matrix would look like this. I will explain later why this is the way we write down this matrix. So, okay. Okay, and now let's actually define this matrix in TFC. How are we going to do that? We're going to use the map function, which creates list. Matrix is a two-dimensional list, which is basically a list of lists. So it's going to consist of so it's going to be a list consisting of lists, where each list consists of 20, well, not 24, but len amount of tosses. So how do we write it down? How does the map function work? First, we write down our variable. Let's call it x, and let's write down which values it's going to run through. So it's going to be from 1 to len, comma, and now we write down the function itself. So the function itself is what the lists are going to be. So each function is a list consisting of flips on certain positions in certain positions here. So for example, if you look, if x is equal to 1, we take this list. If x is equal to 2, we take this list. So what we're going to do is run through numbers starting from x and finishing with x plus length minus 1. So if x is equal to 1, then it's going to be flips at positions 1 to 24. If x is equal to 2, it's going to be flips at positions 2 to 25. And that's how we create this matrix. If remember that it's going to depend remember that it's not 24 but len, because we're going to change this. We possibly will need to change this well, decrease this variable later. Okay, as you can see, it displays the matrix 24 by 24, and put a semicolon here so it doesn't show anything. Now we're going to define a list called outcomes, which I will just call O. It's going to consist of second half of the, not second half, but like if we take the first len entries in the flips list, then the outcomes list is going to be the second the next len entries in this list, which if len is equal to 24 is going to just be the last 24. If len is equal to 23, it's going to be 24th to 46th entries. So it's going to be f with index len plus 1 till f with index to len. Let's write that down simply. The list of flips from len plus 1 until 2 times len. Okay, here is the list. You can check that it's working because it's supposed, right now it's supposed to take the last 24 bits, which it does, I guess. Yep. And if it's 23, it's supposed to finish at 46th bit. Yep. Now, one of the most important parts. We need to check that the determinant of our matrix M modulo 2 is not equal to 0. Why? Well, from what I explained earlier, remember how generating the next toss works. You take the sum of the flips on the positions from the tops list, and take it modulo 2. I can't really explain carefully, but all our matrices and like calculations are always going to be modulo 2. So since our goal is to find the inverse of matrix M, which I will explain later why we need to find that, we actually need to have the determinant of the matrix not equal to 0, so it can be invertible, because remember, if the determinant of the matrix is not equal to 0, then it is invertible. So what we do is we decrease the length until it is invertible. Wow. Okay. So our final length is going to be 18. Okay. Now you might ask, how can we work with only matrix 18 by 18 when our initial tabs list, which I will call T, is 24 entries long? Well, I also can't prove it or explain why exactly, but it so happens that the len is going to be more or equal to the actual size of t, or our list t, if we remove the first zeros from the list. So for example, if t looks like this, we can actually only work with this part, which is exactly 18 entries long. So it so happens that this part is less than or equal to in size to the length. The creator of the script, denial, shout out to him, is not sure that this is 100% true, but if he is, I think he will let you know, or I will. So we can work with that thanks to this, I guess, hypothesis. Yeah. So what we actually need from this our tops list is not all 24 entries, but actually the first non-zero, actually the last non-zero len entries. And we're going to omit this and only work with 18 entries, because the first 6 are going to be zeros. Okay. Alright, so now it's time to explain why matrix M has this exact looks like that. So if we take matrix M and multiply it by our tabs list, we're going to get exactly the outcomes list. Why is that? If we take the first, so you're supposed to know how multiply matrix with vectors work. So the first entry of the outcomes list, which is this entry flen plus 1, which in our case is equal to f19, is equal to, if we multiply the row 1 of matrix M by the tabs list, which is going to be f1 times tab 1 plus f2 times tabs 2, and so on, f18 times tabs 18, which is exactly the definition of how we generate f19. So yeah, because tabs can only be 0 or 1s, everything that is not 0 is going to cancel out. Everything that is 1, everything from the tab list, everything where the tab element is equal to 1 is just going to add up together. So for example, if tab 2, tab 5, tab, I don't know, 17 is equal to 1, then the result here is going to be f2 plus f5 plus f17. Yes, that is exactly how we generate the next toss, as I explained in the beginning. Okay, if we take the second entry in the outcomes list, which is going to be F20th, it's going to be row 2 of the matrix multiplied by the tabs list, which is going to be F2 times tab 1 plus F3 times tabs 2 and so on. F2 19th times tabs 18. The definition of how we generate F20. So thanks to this structure of the M matrix, we can actually create this equation because it fits the definition of how we actually generate the outcomes. Okay. Now we actually need to find this tabs list because we don't know it. How are we going to do that? What we need to do is multiply this equation by inverse of M on the left. We can do that because M is invertible, because its determinant is not equal to 0. These cancel out, and this is what we need to do. To find tabs, we need to multiply inverse of matrix M by outcomes. Now we need to find the inverse of matrix M. The way we're going to do that is using this formula. Okay, first I'm going to just write down the for a normal matrix without any special things that we do in this particular module, like normal formula. It's going to be adjugate of matrix A divided by its determinant. Adjugate matrix of A looks like this. So this is okay. I will okay. I will write it down like this: B11, B12, B1n. I'm going to explain in a moment what it means. And this whole thing is supposed to be transposed. So the element of this matrix Bij is equal to determinant is equal to -1 to the power of I plus j times determinant of the matrix that we get in our original A matrix. If we delete the row number I and column number G. So basically, so it's basically this matrix. Basically, we delete row number I and column number G and get results in matrix. It's determinant of that matrix. Okay, in our particular module, this whole thing simplifies because as you remember, determinant of m modulo 2 is equal to 1, so it's actually only equal to adjugate of m. And all we need to do in our TFC script is actually write down the formula for element, for this element, and then we can just define, and then once we get a formula for each of these elements, yeah, we can create a matrix out of it and then transpose. So let's do that. So okay, let's define the formula, because we will need to, because the way we will create our inverse matrix is going to call for this formula a lot of times, so just need to define it earlier in the script. Okay, so the arguments that we're going to use are the matrix itself and ij. Okay, so it's going to be -1 to the power of I plus j times determinant of this matrix. How are we going to write it down? So there is a function called subset, which basically takes the part of the matrix that you want. Its arguments are the matrix itself and indexes. So indexes vertically are going to be starting from, indexes vertically are going to be from 1 to length excluding I, and indexes horizontally are going to be 1 to length excluding j. So what we actually need to do is write two lists which have all elements from 1 to length excluding I and excluding j. So we're going to write two lists of indexes for 2 dimensions. First dimension is going to be concatenation of from 1 to I -1 and I plus 1 ending with len. And the second dimension is going to be 1 till j -1 ending with j plus 1 until len. So concatenate function just concatenate two lists, which in our case these two lists, and here it's these two lists, which just makes it list 1 2 3 4 5 j -1 j plus 1, sorry, I -1 I plus 1 and so on until length. And here it's 1 2 3 4 5 j so on j -1 skipping j plus 1 until length. So it's going to take this part of the matrix, 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 and make it a smaller matrix with sizes len -1 by len -1. Okay, and of course we modulate this by 2. So basically in this module you can get rid of this part, because it doesn't matter if you modulate this in by 2. But I added it anyway just for proper explanation. Now we need to create the matrix, the Adjugate matrix out of this elements, like, yeah. So let's call it C, and we're going to again use the map function, but this time twice. So map inside of map. So for I, which we're going to run from 1 to n, we're going to use our function is going to be another map, which is going to run j through 1 to n, which is going to result in this element. So basically what we do, this inner map function creates a list for each j that returns this element. So basically it returns, so this inner map function returns a row number I consisting of len elements, because it runs j through 1 to len and returns these elements on I row. And then the outer map function runs the row number, this one, and returns, and for each I returns this row. So basically it returns len number of these rows, creating a matrix that way. Okay, and now I need to figure out why the code is incorrect. Okay, probably because of parentheses. Okay, so I'm actually going to hash that first, and this first, add the parentheses. Yes, add modulo 2. Now it's going to take a while to actually get the answer, so we're going to wait a little. And here's our C matrix. Let's do Shift Tab to actually get this. Oh, I'm sorry, this is not the point yet. First, we actually need to, before we do Shift Tab, we need to find the tabs list. So tabs is just going to be transposed S, C, because remember, it's Adjugate is supposed to be transposed, but the matrix C that we got is not transposed. So transposed C times, so we're using this formula here, transposed C times outcomes. Modulo 2. Okay, let's go. Okay, something is wrong. Oops. Okay, here is our tabs list. As you can see, the first entry is 1, which is predictable because we got rid of first 6 zeros. Okay, now let's actually do Shift Tab on the tabs. Okay, and we don't need this portion of the code anymore. Okay. Now all we need to do is get the next 11 flips. To do so, we multiply this. We will multiply them. We multiply, as I explained earlier, tabs with the last len entries in the flips list. Okay, so let's do that. So tabs multiplied by. Okay, and now we're going to write it down the fancy way. So flips. We're going to run the index in this list from the size of the flips, which is the last position, minus length plus 1 until the size of the flips. So essentially the last len number of entries in the flips list. To write it down, we need to do the size function of flips, which by the way, size function, it returns a list, not a number. So if we for example try to find size of a matrix, it returns a list of two numbers, which are dimensions of the matrix. If we find out the size of a list, it returns just the length of the list, a list consisting of one number. So we're going to do that, which is basically taking the first entry in the list, which is by itself only one entry long. So this thing should return us at this point 48. And by the way, if we don't do that, it will just show a list. As you can see here, it's a list, not a number. Okay, minus len plus 1, and the finishing value is going to be just the size of the flips. So once again, this is the minimal value, this is the maximum value that we run through the index. So flips is going to, so the tabs are going to multiply by the last len entries of the flips list, and as always modulo by 2. And all we need to do is just keep adding the result at the end of flips list. 1 1 0 1 0 0 0 0 0 0 0. Okay, I believe we have 11 flips, tosses. Okay, this is redundant. Okay, this is our answer. Okay, how do we submit it? To enter the submission mode, you press this button, hold. Okay, and now, as the manual says here, holding the losing bar submits heads, which is the 1. So to submit 1, you hold this thing. To submit a 0, you hold this thing. Okay, let's go. 1 1 1 0 1 and the rest is zeros. And when it's solved, you just need to hold once again this button to submit the module. And this is how you solve the module. Thanks for watching, and I hope that helped you to understand why the script works like that, because if you don't, you will actually probably not be able to replicate it if you need. But to actually solve it on profile bombs or Twitch plays, once again, you don't need to replicate the script, you can just use it. Anyway, thanks for watching and have a nice day.